Hi, dear students. After the break, now it is the time to talk about chamfers rounds and fillets and chamfers. Okay, first see the definitions. Which feature is called chamfer? Which feature is called round? Which feature is called fillet? Okay. Well, rounds and fillets and also chamfers are well along an exterior edge mainly are to prevent possible hand cuttings. Explain what I mean. For instance, that is the object, and this edge you see is a sharp edge. It is formed by this flat surface and that flat surface, and you see this edge is uh, a sharp edge. Well, if the body is a heavy object, and if in the design of the object the edges are sharp edges, whenever someone attempts to hold the body with Nike hand, for instance, a worker hold this object with Nike hand, well, along this edge. This edge will behave as if it were a knife edge, and since the object is a heavy object relative to the strength of the skin of hands, well, probably this edge, such an edge, will cut the hand and cause to injuries. Okay, to be able to prevent being in such a case possible hand cuttings, the best solution is rounding. Cut the material along the edge, round it in cylindrical shape. While cutting the material, if you have a cylindrical surface along the edge, then rounded edge cannot cut hands. Rounded into exterior edge, such an edge, rounded exterior edge is called round. Okay, it is the best solution to prevent hand cuttings. How about fillet? Fillet is a rounded edge, a rounded feature. It's a cylindrical surface created along an interior edge. Okay, well, round this edge, for instance, this edge. Now I'm using the tools of inventor, by the way. Clicked on this button and then write the rounding radius, say that it is 5 into the box. Later gonna practice on rounds and fillets in inventor. This is just for the definition part, for demo purpose. Okay, and then indicate this edge. This edge, for instance, at present is a sharp edge. Indicate it, and then you see it is about to be rounded. Clicked on apply. Yes, now this edge cannot cut hands. Round this edge. Okay, and then say apply. Clicked on this. If we round the edges, well, those cannot cut hands. It is the best solution. But if we round an interior edge, this is an interior edge, round it. Why? Well, interior edge cannot cut hands, although it is a sharp edge. Although it is so, why it is strongly recommended that the edges are to round? Well, the reason comes from the strength of materials. If an interior edge is a sharp edge, whenever the object is loaded by the external forces, then along the sharp edge, well, the atomic bonding forces within the body will tend to go to infinitely, tend to take infinitely large values. Since it is impossible, the result will be a failure, object will be broken. To be able to prevent excessive stress within the body along a sharp interior edge, this is the recommendation. Round the edge. If you round the edge, then, well, stress means atomic bonding forces per unit of area. In engineering we use stress, not force, but we use force per unit of area. We use stress means atomic bonding force divided by the area of the surface in consideration. Well, rounding an interior edge, we prevent having excessive, very great stress values within the body, and via which can prevent the weakness. Okay, sharp edges cause the weakness. If you round the sharp interior edges, then, well, this means we achieve to prevent failure. It's going to be, body will be more strong along the edge. Well, rounded exterior edge is called round. Rounded interior edge is called fillet. This is a fillet. How about chamfer? Chamfer is an alternative process. It is applied, chamfering process is applied along an exterior sharp edge. Okay, via cutting the material, okay, can create an inclined surface along the edge. It is again to decrease the level of risk of hand cutting. Well, at present, for instance, this edge is formed by this and that, those surfaces, and the angle between them is 90 degrees. So for this exterior edge, sharpness angle is 90. Sharpness angle is 90. If we decrease the sharpness angle, then sharpness increases, so the hand cutting risk correspondingly going to be higher. Risk also will be increased. If we increase the sharpness angle, the limit is 180 degrees, then there will be no edge, there will be no hand cutting risk. So in this regard, chamfering process finds its logic, finds its meaning. Well, let me take a pointer into my hand. Well, there is a software here. I'm going to run the software. Okay. And then take a marker into my hand, and then okay, at present, well, the sharpness angle for the exterior edge is 90 degrees. Well, measure such a distance over the surface, measure the distance over the other surface, and then after marking these points, well, cut the material along this edge. Well, create an inclined surface. It is not a rounded surface, it's not a cylindrical surface, but it is a flat surface. If we do this, well, at the end there will be an inclined surface along the edge, and the sharpness angle will have not one intersection but two intersections after cutting the material. For both, the sharpness angle going to be greater than 90. If the sharpness angle is greater than 90, you see these are obtuse angles, then this means the hand cutting risk will be less. Okay, that is the motivation, that is the logic in creating chamfer. Chamfer is an inclined flat surface. It extends along an edge. It is to prevent possible hand cuttings. It is a cheaper solution relative to the cost of rounding process. Well, chamfering is cheaper, but the hand cutting risk won't be 0. For a round, hand cutting risk is 0, but if there is a chamfer along the edge, then hand cutting risk will be less, but it won't be 0. It's a cheaper solution, but the risk elimination is not in the order of 0%. Elimination percentage is not 100, but less than 100%. Okay, then, well, create a chamfer along this edge. Well, in Inventor, that is the push button to click to start the process. Well, I am going to create the inclined surface. It is inclination angle going to be 45 degrees. So, well, chamfer distance over the surface, over that surface, is the same. Let's say 4 millimeters is the chamfer distance. And then indicate the edge. Yes. And then say OK. You see, now along the edge I created not a cylindrical surface but a flat surface. It is called chamfer. OK. And then see the chamfer sharpness angle. You see this angle is obtuse, that angle is obtuse, and the risk level is less, hand cutting risk is less. Chamfer, fillet, and round. Okay, after this definition stage, then yeah, okay, turn back to our example and then see how a round is created, how a fillet is created, how a chamfer is created. Similarly, along the ribbon in AutoCAD, which ribbon? Solid ribbon, can find the facilities, fillet, rounds, and the other option is to create chamfer. Clicked on fillet edge button. Okay, and then, well, to be able to teach the software that rounding radius is equal to that much, clicked on down direction key and then select radius option. And the default value is 1 millimeter. No, not 1 millimeter, but rounding radius, say that is 8 millimeters in this example. Press enter. And then indicate the edge. Well, along the edge of the cylinder, let us round. Okay, indicate the edge. And then, well, right click the mouse and then select enter option. Yeah, you see along the edge we have a round. How about filleting? Well, use the same facility. Okay, rounding radius, select down direction key of the keyboard, click on. If you have a tiny arrow within the compartment, it implies that there are some options. Clicking on the down direction key of the keyboard can drop the list of the options, and from the list select radius option, and then radius is into the box right, say that it is 8 millimeters. Press enter and then indicate the edge, this interior edge, and then enter. Yes, twice clicked on enter, or right click the mouse and select enter option. Well, it is what? It's a rounded edge. Well, this is called fillet. The one we created the rounded surface along this exterior edge is called round. How about chamfer? Well, drop this list of the options and select chamfer option. Okay, well, before indicating the edge, well, in this example, I'm going to create a chamfer along this edge. Clicked on down direction key and then select distance option. Okay, specify distance 1. Well, first distance is to measure over one of the surfaces, the other distance over the other surface. These are the surfaces, intersecting each other, forming the sharp edge at present. Okay, first chamfer distance is, let's say, 10. Press enter. And now within the compartment, AutoCAD asking the second chamfer distance. If the inclination angle of the inclined surface chamfer is 45, then the second distance must be equal to the first distance. But if the chamfer distances are different, over a greater size surface, the chamfer distance may be greater. Over a smaller surface, it is to be normally smaller. Okay, the top surface is greater in size, so I said that over that surface, chamfer distance is 10. The vertical surface is smaller in size, so well, second chamfer distance, not 10, but say that 6 millimeters. And then press enter, and then, well, system saying that where is the edge, indicate the edge, indicate this edge. And then, well, see this simulation. Well, in this direction, zoom in. Yeah, yes, AutoCAD in the simulation says that, well, the larger distance is to apply over which surface? Well, I said that first chamfer distance, although I expect to find the first chamfer distance as measured over this surface, but unfortunately, well, AutoCAD measured the longer distance over the small size surface. So, well, if the order is wrong, then obvious to be able to have the chamfer distances as measured on the correct surfaces, well, change the order. Press escape button, cancel this attempt, and then repeat the chamfering process. Okay, well, down direction key, select distance option. First distance, well, I see that AutoCAD measured the first distance over this smaller surface. So first distance is 6. Press enter. Second distance is measured over this surface. It is 10. I changed the order, you see. Press enter and then indicate the sharp edge. Then yes, well, the chamfer distances measured on the correct surfaces respectively, and then the rest. Enter, press enter twice. That's it. You see, along the edge there is an inclined surface. If such an inclined surface is to create if the inclined surface is to create for preventing hand cutting, then it is called chamfer. And in English we say chamfer, in Turkish pah. The cutting process is called for creating a chamfer is chamfering. It's called chamfering. In Turkish pah kırmak. Pah in Turkish, chamfer in English. Name of the process chamfering. Name of the process in Turkish pah kırmak. Don't say pah yaratmak. Say kırmak. Pah kır. Okay, then completed this classwork. So in the order, save the file saying classwork 4, I think. Yeah, yes, blah blah CWV4, October 29, OCT 29. Okay. And then, how about oblique surfaces and oblique surface creation? First, study on the definition part. Saying oblique surface, we mean what? Okay, for defining what it means, I'm going to use this file. Yes, it is about to be visible. It is the object. Okay, and visualization style shaded with edges. Okay, if a surface is parallel to the picture plane, projection plane, it is called, well, principal surface. Front side is a principal surface. It is called frontal surface. Top surface, bottom surface. Top and bottom surface parallel to horizontal picture plane, so these are in general called horizontal surfaces. But if a surface is not parallel with respect to, not parallel to the principal picture planes but inclined, then it is called inclined surface. An inclined surface will be perpendicularly oriented with respect to the third. Okay. See such surfaces. For instance, this surface of the object is parallel to the frontal picture plane. It is called frontal surface. That surface is parallel to profile picture plane. It is called profile surface. Well, that surface is parallel to the horizontal picture plane. It is called horizontal surface. Okay. How about this one? The surface of the channel, this surface, you see is inclined with respect to horizontal, with respect to the profile. But it is perpendicular. See the orientation. That surface is perpendicular with respect to the frontal picture plane. Well, it is in general speaking called what? An inclined surface. This is an inclined surface. Okay. But if a surface is inclined with respect to all the picture planes, an inclined surface inclined with respect to two of the picture planes but perpendicular to the third. This inclined surface in the example is perpendicular with respect to the frontal picture plane, this. But if a surface is inclined with respect to not two but three picture planes, three of the picture planes, with respect to all the principal picture planes, well, for instance, this surface is inclined with respect to the horizontal, with respect to the frontal, with respect to the profile picture plane. It is called oblique surface. Okay, this is an oblique surface. And to be able to define a surface, flat surface, you know, from the geometry, 3 points are sufficient. Okay. Well, 3 points can fully define a flat surface. To be able to define the orientation of an oblique surface and thereafter to create an oblique surface, correspondingly need to use 3 points. Well, for instance, if you know the coordinates of this point, it may be one of them. Coordinates of this point, it is the second point, and coordinates of this, it is the third point. Okay? These 3 points, using these 3 points can define the inclination, orientation of the flat surface, the oblique surface. Fully define it. So, since it is so, well, the creation method in AutoCAD and also in Inventor, well, we use 3 points. if the locations of 3 points are given or specified, then step by step, of course, passing to the stages, in the end can have create an oblique surface, can have an oblique surface. In AutoCAD environment, to create an oblique surface, may have two different cases. If the oblique surface is to create at the corner where the surfaces are perpendicular to each other, this edge, for instance, perpendicular to that edge, then yes, can start the polyline process, but first, locate the origin of the coordinate system at the corner where indent going to have an oblique surface, and then using the coordinate system, origin is at the corner, when we orient the x-axis as coincided with this edge, then y-axis going to automatically coincide with the other edge, because the angle between the intersections is 90 degrees, and the third axis, may be z-axis, coincide with the third. Then using such a coordinate system and starting the polyline creation process in 3D, we can draw the boundaries of the oblique surface, and then indicating the area, it is a region bounded by these boundaries. Apply extrusion process. After creating a triangular prism, then by subtracting it from the rest of the body, indent can create an oblique surface. That is the thing to do in AutoCAD. But if the angle between the intersections is not 90 degrees, then although we coincided x-axis with one of the edges, then the y-axis will not coincide with the other edge. In such a case, before creating the sketch via using polyline facility, it is going to be a must to mark the corner points of the oblique surface, and then join the points with the joining lines using polyline facility. I'm going to illustrate the stages for both of the cases, and then all the things I think going to be clear enough. Close this file. And then turn back to our example. Open the file. Which file? See their names in the list. I set classwork for OCT 29. Classwork 1, classwork 2, classwork 3, and classwork 4. Yes. And then continue. Sorry. Now I am sure the angle at this corner between the surfaces is a right angle. Here it is the H. This intersection is perpendicular with respect to this intersection. So at this corner create an oblique surface. Well, without marking the corner points we can do it because the angle between the surfaces is 90 degrees. Okay. First, since I know the coordinates of the corner points with respect to this corner, I am going to move the coordinate system, okay, to this corner. You know how. Clicked on this button, and then, well, while this surface is being highlighted, indicate this corner as the origin, indicate this point as the point along the x-axis, and indicate this point to coincide the xy plane with this surface. And you see, since the intersections are perpendicularly oriented, when I coincide x-axis along one of the edges, then y-axis can automatically coincide with the other intersection. Okay. And then, since the coordinate axes are coinciding along the edges, well, without marking the corner points, I can create the boundaries of the oblique surface. Okay, along the x-axis, well, I'm going to write the coordinates of the corners. Well, abscissa value of this point, abscissa value of this point, abscissa value of the third point, ordinate values, altitude values. This is, say, that point 1. For point 1, it is this point, let's say. For point 1, the abscissa value is, I don't know, say that 80 millimeters. Okay, relative to this origin, ordinate value is 0. Altitude value is also 0. Okay, second point is this one. Now the location dimensions for the second point with respect to this origin, say abscissa value is 0, you see. Well, for all the points along this edge, abscissa is equal to the abscissa of origin, and it is 0. Ordinate value, say that is 70. Okay, and altitude value for this point is 0. For the third point, point 3, abscissa value is 0. Ordinate is 0. Altitude is, let's say, 100 or 120. These are the coordinates of the points with respect to this origin. Okay. Oh well. I forgot the numbers, but by mistake I deleted them. Say undo, and then, well, take an eraser and clean this part. First point, second point, third point, and then start the process. First point, 80, 0, 0 coordinates. Okay. Well, polyline, not single but polyline. But here, well, in drawing panel, this is 2D polyline facility, and that one is 3D polyline. Well, since the points to mark are not in the same plane, well, the polyline is a 3D polyline. So start the process clicking on 3D polyline option. And then, well, after starting the process, system asking the coordinates of the first point relative to the origin. For the first point, the reference is the origin. And I remember the abscissa is 80. Clicked on comma key. Ordinate is 0. Clicked on comma key. Altitude is 0. Press enter. And then, yes, the first point is over there. And then the second point, well, be careful. For the second point, abscissa 0 relative to the origin, altitude is 0, ordinate is 70. But the values, since dynamic input button is on, dear students, well, for the second point, the values, well, I'm going to write these coordinate values on a piece of paper, dear students, because, well, when I close the marker, then the values disappear from the screen. For the first point, abscissa relative to the origin 80 by 0 by 0. For the second point, 0, 70, 0. For the third point, 0, 0, 120. Okay. But here, after marking the, dear students, marking the first point, then write the coordinates of the second with respect to not the origin, but with respect to the first point. Okay, the coordinates of the second point with respect to the first point, well, although abscissa is 0, but relative to the first point, the abscissa is minus 80. Okay, minus 80. For the second point, abscissa is minus 80. Why minus? Because from here to there, while displacing, well, it's parallel to the x-axis, the displacement will be 80 millimeters. But since the displacement toward the negative side of the x-axis, you see x-axis, positive center of the axis is in this way. But the displacement from here to there, for having the first boundary of the polyline, for having the first boundary of the sketch, while the displacement from here to there is in the negative sense of the x-axis. So abscissa for the second point with respect to the origin is 0, but with respect to the first point is minus 80. Okay, well, while moving from here to there, the ordinate value will be 70, altitude value 0. Okay, with respect to second point, the coordinates of the third point, okay, well, you see abscissa value from here to there, since the displacement is in YZ plane, the relative abscissa value going to be 0 for the third point. Relative ordinate value going to be minus 70, because while moving from here to there, assume that it is like a path and you're traveling or walking along this path, your displacement as parallel to the y-axis going to be 70 millimeters. But since the displacement is in the negative direction of the y-axis, 70 must be written as negative. Okay, minus 70. And the altitude, z-axis, is in the up direction, while the distance from here to there is 120, but the displacement is in the negative sense of the z-axis, so write minus 120. Okay, the Coordinates of the first point with respect to the origin 80, 0, 0. Coordinates of the second point with respect to the first point, not 0, 70, 0, but minus 80, 70, 0. And the coordinates of the third point with respect to the second, well, abscissa 0, ordinate is minus 70, altitude is minus 120. Keep these numbers in the mind. Okay. And then, yes, start the 3D polyline process. For the first point, well, abscissa is 80. Clicked on comma key. Ordinate is 0, comma, ordinate altitude is 0. You see, AutoCAD uses the same colors within the boxes, those of the coordinate axis. X-axis is red in color, and the abscissa box is red. Ordinate axis green, while the box to write the ordinate is green, you see. And altitude axis is blue, and the fourth compartment is the compartment to write the altitude value, has a blue background color. Okay, altitude for the first point, it is along the x-axis, along the edge, the x-axis coincide is 0. Write 0 and press enter. Okay, that is the first point. Well, sorry, do it again. Say undo. I made a wrong click. Well, abscissa is 80. Clicked on comma key. Ordinate is 0, comma, altitude is 0. Press enter. And then the second point. Well, write the coordinates with respect to the first point, with respect to the preceding point. Abscissa is minus 80. Ordinate is 70. Clicked on comma key. Altitude is 0. Press enter. Yes, you see I have a joining line. The first boundary of the region which extends from the first to the second. And the relative coordinates for the third point. Abscissa 0. Clicked on comma key. Ordinate is minus 70. Clicked on comma key. Altitude is minus 120. Press enter. And then, well, the third point, well, third boundary line, well, I'm going to use snap technique. Well, indicate the starting point, first point, as the ending point of the third joining line. No need to write any coordinate value. Press escape button. Here is the sketch. Okay. And then the rest, apply extrusion process. Well, when I bring the cursor to the vicinity of the sketch, you see other intersections, equal likely attempting to snap my cursor. So for my convenience, I'm going to change the style to wireframe and much more easily indicate the sketch. Start the extrusion process, indicate this sketch, press enter, and then create the prism toward the atmosphere. Its length is not so important because this prism is to subtract from the rest of the body. It is to use for creating an oblique surface. Okay, and then see the things shaded with H. And now, well, see what we have. We have such a triangular prismatic extension. Okay, and then Boolean algebra subtraction. Start the subtraction process, indicate the main part, press enter, indicate the newly created prism, press enter. Yes, you see after subtraction over there what we have the oblique surface. Here it is, the oblique surface. Let me shoot the coordinate frame back to its word location. Much more clearly can see the oblique surface. Yes, managed to create the oblique surface. Visualization style, you know the trick. Warm, cool face style, and then realistic style. Surface is in the color of the line, layer of the line. Say line of the layer. It is green. Well, you need, we need to assign the material for the surface as well. Hold the material option, press polished, and drag the mouse toward the surface and release the button. Release the button. Okay. Here is the oblique surface. Managed to answer the question how an oblique surface is created. Okay, save the file. Saying classwork 5. Save as. Okay, classwork 5. Well, if the angle between the intersections is 90 degrees, oblique surface, in creating the oblique surface, no need to mark the points. Directly start the 3D polyline creation process and then be able to write the coordinates of the corner points relative to the preceding one. For the first point, preceding point is the origin. Can directly write the given coordinate values, but for the second and the third points, well, be able to write the relative coordinate relative to the preceding point. Write the coordinates of the second point with respect to the first point. Write the coordinates of the third point with respect to the second point. There is such a trick. Okay, it is quite important, dear students. Okay, and then, the following example, after the break, I am going to create it. For having an oblique surface at this corner, the inclination angle between this edge and the other edge is not 90 degrees. Since it is not 90 degrees, then, in the method, we need to mark the corner points first and then apply the boundary line creation process, 3D polyline process. Okay, after the break, you're going to see how. Okay, dear students, have a break now and then continue. Yes.